Hello and welcome to this session for Discover University. I'm Joanna and I'm going to be taking you through some of the basic physics behind motion. So we're going to look at Newton's laws of motion and also at the conservation of energy. We'll then be taking some of what we've learnt and putting it into practice. So we'll start off with Newton's laws of motion. Newton's first law of motion states that if the forces on an object are balanced, that object doesn't change its motion. For instance, consider a ball sitting on the ground. The force of gravity is pulling it down, but the force of the ground is also pushing it up. Because these two forces are equal, the net force is zero, so the ball does not change its motion. Now we'll consider a ball falling under the force of gravity. So it still feels the force of gravity, but it doesn't have the ground pushing back, so therefore the forces are not balanced. This object does change its motion, it accelerates downwards. Newton's second law states that the force on an object is equal to its mass multiplied by its acceleration. We can write this as an equation like this. Force equals mass times acceleration. F equals ma. This means that the larger the mass, the larger the force, and the smaller the mass, the smaller the force. Acceleration due to gravity does not actually change dependent on the mass of the object. This means that if you dropped a bowling ball and a feather in a vacuum, so there was no air resistance, the two items would actually land at exactly the same moment. However, due to Newton's second law, the bowling ball would hit with considerably more force. Newton's third law states that for every action there is an equal and opposite reaction. If we consider a ball dropped onto the ground, the ball exerts a force onto the ground at the moment it hits. However, the ground also pushes back with an equal and opposite force. So the ball hitting the ground is the action, the ground pushing back is the reaction. Here is a brief recap of Newton's three laws of motion. Now we'll move on to conservation of energy. The laws of conservation state that energy can neither be created nor destroyed. It can only be converted from one form to another. There are numerous different forms that energy can take, as you can see from the list below. As an example, we'll consider a wind turbine. This converts kinetic energy from the wind into electrical energy. There is also some energy loss through heat and sound due to friction and air resistance. So, now that we've covered the theory, it's time to get down to the fun stuff and put that into practice. We're going to be looking at Rube Goldberg machines. Rube Goldberg was an American cartoonist in the 20th century. He's best known for designing machines that were a complicated way of doing very little. So, for instance, it would pour a bowl of cereal or turn a light on, but through a whole series of preposterous and overly complex methods. If you think perhaps of the game Mousetrap or of the inventions of Wallace and Gromit in their cartoons, you'll get the idea. Another such cartoonist was Heath Robinson here in this country, and his name is also synonymous with inventions which are overly complex. So, in true Blue Peter style, here's one I made earlier. So, in this machine, the marble runs down the tube, which converts gravitational potential energy of the marble into kinetic energy. It then knocks over the first domino, which in turn knocks over those following, transferring kinetic energy from one to the next. The last domino lands on the launcher, releasing the elastic band and firing the toy car forwards. This uses the kinetic energy from the domino to release the elastic potential energy from the elastic band, which is then converted into kinetic energy of the car. After that, the car runs into a wedge-shaped block, which tips over the cereal box, transferring the kinetic energy of the car to the cereal box. This allows the cereal to fall, converting its gravitational potential energy into kinetic energy. Once more in slow motion. Now that you've seen what I made, it's over to you. You're going to build your own Rube Goldberg machine at home to perform some simple tasks such as putting a ball into a bucket, pouring a bowl of cereal like mine, opening a door, turning a light on, something like that. Okay? Remember that once your machine has started, you can't touch it. So it needs to do everything by itself once you've released the initial trigger. I'd like you to put in at least 3 steps. So at least the opening step, something in the middle, and the final result. And make sure you ask permission first, don't use anything you're not supposed to, and that you clear up afterwards. Okay? So, a few tips to get you going. Start simple. You can always make it fancier as you go along, but if you start off too complicated, then you're going to tie yourself in knots. Make sure that it's repeatable. You're probably going to need to run this a lot of times before you get it completely right. So you need something that's easy to reset. Make sure you do it one step at a time. So I found it's easiest to start at the last step, the result you want, in my case, pouring a bowl of cereal, and then work backwards from there, adding one step at a time. Remember the physics. So, you're going to be converting energy from one form to another, and sometimes it won't work straight off. But if you go back to the physics of it, then you should be able to work through and solve your problem. Remember that most things don't work first time. The more complex they are, the less likely they are to work first time. This is something engineers face day to day in their work. So, problem solving is a part of the job, is exciting, frustrating, and essential. So just keep at it, keep trying, and if necessary, tweak, rethink. Okay? So, good luck. Make sure that you put up photographs or films of what you've done. We'd love to see it. And have fun. Bye.